works into the role of time series. So a little bit more on my background. I know Bill sort of laid it out for you guys a little bit. I have a PhD in statistics from North Carolina State University, where I also currently work. And that PhD in statistics was focused on the idea of financial statistics around the notion of time series, really volatility modeling, but also time series in general. And so I have a lot of experience in working with the idea of time series. And so I wanted to try and build out people's tool belts, for example. There are so many different ways you can do time series out there. Unfortunately, not a lot of people know about the Bayesian approach to time series. So really what I wanted to do today in this webinar is really try and connect all the concepts of time series in general, what we typically think of as time series, and how the Bayesian approaches to time series intersect with those. So let's jump in, let's have a little fun, and let's talk about Bayesian time series today. As always, feel free to ask questions throughout. I'm monitoring the chat as well. Now, it's one of those things where if the questions start coming in too rapid fire in the chat, I may miss one here or there. So if I do, please forgive me. Just hold it off to the end. And you guys are welcome to connect with me. I'm an easy person to find online, probably just because my name is spelled so uniquely. So that being the case, feel free to reach out on LinkedIn. You can find that on my website as well. Feel free to connect. Awesome. So let's talk. What is time series? Well, just to make sure we're all on the same page and have the same foundation on what we're talking about when we talk about time series, let's revisit what is time series. So a lot of the data that people will typically work with is what we call cross-sectional data. The notion where we have basically data, again, in individual rows. But these rows are what we think of as independent observations. Each row represents one person. Each row represents one object, something along the lines of an independent measurement that we're looking for. Now, when understanding these independent measurements, maybe we have some target variable, something we're interested in. Let's call that y. And when looking at y in a cross-sectional standpoint, we're typically looking at y from a distribution, something like you see here. We have basically a distribution of y. Here we're looking at the distribution of consumption, and we're just, again, trying to understand what consumption looks like. Now, of course, we're not going to just look at y by itself. We have all of these other variables available to us. And so again, in cross-sectional data, you can think of all of the columns that we have as potential predictors or explainers for what we're looking at in our target variable y. And so what we do is we typically try and relate these things together, right? So I have all of these x's. And so let's say we have an x and we're trying to relate it to y. One way of doing that, again, when we have cross-sectional data, is sort of just looking at a scatter plot. Right, so we have personal income in terms of percentage change, and we're comparing it here to US consumption with the idea that as personal income goes up, people consume more. Time series data, on the other hand, is a little bit different in how it's structured. We don't think about it as each row as an independent observation. In fact, we take advantage of the fact that they're not independent observations. A lot of our rows when it comes to time series really are this idea of, well, time. They're this notion that we're measuring the same object, same person across many different points in time. So we're seeing time and we're seeing this object evolve over time. So again, taking something like US consumption as a target variable we may be interested in, we can see something like you have here on the slide. We can see the evolution of US consumption over time. Each one of these points is not independent of the other points. In fact, there's probably this relationship that exists just due to the passing of time. What US consumption is today probably depends on the US consumption was last quarter and the quarter before that and the quarter before that. And so we have this evolutionary process of this object that we're interested in. Now, of course, we don't have to just look at this object by itself in a vacuum. We can, again, relate these other variables I was mentioning to this target variable. And so we can do this here. I've shown you guys just an example of a cross correlation chart, really trying to correlate the idea of personal consumption as well as personal income at different lags of time. The idea being, if income increases this quarter, do we see consumption also increase this quarter? Or is it something that we see lag behind? That's the idea of how we can relate things in a time series. So again, the main idea of this first section is really comparing cross-sectional data, which is what a lot of people are used to dealing with the nuances and the differences of time series. So now that we all have sort of time series under our belts, let's compare real quickly the idea of a frequentist approach to statistics to a Bayesian approach to statistics. And what better way to understand anything in the world of mathematics or statistics than to go to good old xkcd.com, right? You know, I can't think of things that are better than this when it comes to jokingly trying to explain differences in mathematics. So I'm going to give you all a moment just to be able to sit here and see what this comic is. For those who may have a little bit of a hard time seeing it, depending on the device that you have, the main idea is this. The question that is posed by this XKCD comic is, did the sun explode? And then you basically have two people here. These two people have a device that tells us whether or not the sun explodes, but it compares it to a random roll of a die. And so either one, a random roll of a die could occur, or the sun has exploded. The frequentist statistician calculates the probability of seeing this occurrence, the machine telling us that the sun has exploded or that the random roll of the die has occurred. And since this probability is less than 0.05, they conclude the sun is gone. The Bayesian then, you know, the idea of the Bayesian inference here and sort of the joke is the Bayesian goes, I bet you $50 it isn't. And that's sort of the idea. When looking at the differences between a frequentist approach to things and a Bayesian approach to things, it's really a foundational difference in how people view things that you're trying to estimate. Coming from one of the largest graduate programs in statistics in the United States, NC State has both frequentists and Bayesians in terms of its faculty. In fact, I remember back when I was a student, I had PhD Theory 1 taught by a frequentist, and then PhD Theory 2, day 1, a Bayesian professor walked in and said, everything you all learned last semester was completely wrong. Let's start again. And so there are different views of how to be able to approach statistics. And really trying to boil it down in a very simplistic way, the view revolves around what you see here on the screen. A frequentist view of a parameter is basically an unknown fixed point that we're trying to be able to estimate, we're trying to be able to guess. While a Bayesian view of this parameter that we're trying to estimate and guess is it's a moving object, essentially some notion of something that is moving, but it has a known distribution of how it moves. That is, again, a very simplistic breakdown of the difference between a frequentist and a Bayesian. Again, the way I like to sort of try and explain it to people who may not know the difference, imagine you were going fishing. Do you believe the fish is standing still and you just throw out many different nets or many different lures and hope that it drops in front of the fish? Or the Bayesian approach would be the fish is moving, however I know how it's moving, so I'm going to throw out one lure or one net and figure out the chances of it coming to that lure. That's the difference between a frequentist and a Bayesian. I don't want to make it seem, though, that Bayesians don't use data, because Bayesians do. They just have a predisposed approach to what things are looking at. You have a prior distribution. Think about, this is what I think this object is moving like. Again, I think the fish is moving in this way. Let me then add some data to the problem. Let me collect some data and see, oh, so this is how the fish is actually moving. I'm going to combine both of those pieces of information into an updated thought on how things work. That's the idea of a Bayesian approach. You have a preconceived notion of what things are going on as. You add data to that preconceived notion, and together, your preconceived notion and your data form now your new opinion of the situation. That's the idea of how a Bayesian approaches things. A frequentist, on the other hand, approaches everything as a brand new problem. I've got data that comes in. I'm going to use that data to analyze. I do not have any preconceived notions of what I'm going to be looking for. Okay, so again, basic breakdown of the difference between a frequentist and a Bayesian. But if we're going to talk about Bayesian statistics, one thing we do have to mention is the idea of a Markov chain Monte Carlo. The idea of a Markov chain Monte Carlo is this. Well, Monte Carlo is the practice of estimating the properties of a distribution by examining essentially random samples from the distribution. Let me give you an example. Instead of finding the mean of a normal distribution by going and flipping through a statistics book or looking on wikipedia.com and trying to figure out what the actual mean is from a raw equation, the idea of a Monte Carlo approach would be to draw a large number of random samples from that distribution, calculate the average from those samples, and that's going to be your best guess of the average of that distribution. So again, think about like simulation. We're going to simulate a bunch of different possibilities, calculate the average, and that's our best guess instead of drawing out an actual equation. Now, the benefit here of Monte Carlo is actually quite clear from this, right? Calculating the mean of a large sample of numbers a lot of times can be easier than calculating the mean directly from a normal distribution's equation. Now, something simple like a normal distribution, it's probably not going to be too bad to look up that equation. But this benefit is probably the largest when random samples are easy to draw and distributional equations are hard to work with. So it's like, wow, I have this really tough equation and something I can easily sample from. Let's just go with the sample instead. Now that explains the idea of a Monte Carlo piece of what we're doing for Bayesian analysis. But let's talk about the idea of the Markov chain property. So the Markov chain property of the Monte Carlo Markov chain, the MCMC, is the idea that random samples are generated by an actual sequential process. So each sample is used as a stepping stone to generate the next random sample, hence the name chain. Now, a special property of that chain is that each new sample depends only on the one before it. It does not depend on anything before the previous one. That's where the Markov property comes in. So when we're talking about the idea of a Markov chain Monte Carlo, all we're trying to do is we're trying to estimate parameters of a model. So we have these parameters in the model that we're trying to understand, that we're trying to estimate. These parameters have complicated equations. So we're going to sample to get an estimate of these parameters, but we're going to sample in an efficient way. We're going to sample in a Markov style where we're going to be chaining these samples all the way along. So what you see here actually on the screen is an actual display of the chain of samples. So for example, if I wanted to get the parameter estimate, let's say from a simple regression model that relates personal income to personal consumption, what is that relationship? What is that beta estimate? Well, essentially what we're going to do is we're going to draw a sample, estimate that slope, that relationship. Then we're going to draw another sample, estimate the slope, draw another sample, estimate the slope, and we're going to continually do this, but again, in a chain-like sequence. The left-hand chart that you see here is actually a zoomed-in version of the first 100 samples in the chain. The right-hand chart is actually the view of the entire chain, all 20,000 samples that we use to be able to calculate that relationship. So again, the idea here is we're using data that we're seeing. We have some previous concept on how we're going to do this and what the distribution is. And then we're going to sample from this data over and over and over and continually update our thoughts. And then what we're going to do is look at the overall distribution of these samples to see what we think at the end. I'll show you a little bit more as we actually work through a real world example. So let's now compare the idea of classical time series modeling to Bayesian time series modeling. To understand Bayesian time series modeling, you have to know what classical time series models are. The idea of statistical forecasting and time series modeling is quite simple. Really, a time series is where you're trying to extract signal from data. It basically boils down to that, right? You have this data that's evolving over time. We talked about that earlier. So we have this data that's evolving over time, and we're trying to extract signal from this data. Now, we're not going to be perfect, so there's going to be some signal or some data that's left over. We'll call this sort of the noise. Okay, so it's not perfect, but we have some notion of what we're doing. We're going to use this signal to essentially extrapolate into the future. Now, most people don't like the word extrapolation, so let's just call it forecasting, okay? But in the end, it's the same idea. Take the signal, repeat that signal into the future, and that is going to be your forecast. Now, again, we have some idea of noise. The noise that we have left over, our uncertainty, essentially what we're going to use is we're going to use that uncertainty, that noise, to measure some notion of confidence intervals around our forecasts. Essentially, how sure of our forecasts are we? That's the idea. And okay, cool, great. So we have signal, we have noise. All right, so how do we measure signal? Well, one of the most basic ways of trying to understand signal when it comes to time series is the notion that we have this dependency on time, right? We talked about that earlier. If we're measuring consumption across time, logically it would make sense that our consumption a quarter ago was going to be a lot more related to our consumption today than our consumption 20 years ago. And so that's what we're trying to understand. We're trying to understand how these things change over time. Well, a very naive way of trying to do this would just be to take the average, and that average would be your forecast into the future. What has average consumption been historically? And so with that being the case, I'm going to assume that average historically is going to be all the way into the future. Now, that would basically say that everything in the past is meaningful. Now, the extreme other end of that situation would be the only thing that's meaningful is today. Today is going to be my forecast of the future. The past means nothing to me. I could care less about the past. I'm focused only on the future. Today, the value of consumption is this. That's going to be my guess going forward. Again, these are sort of opposites. One assumes the entire past is helpful. One assumes none of the past is helpful. Of course, modern time series approaches try to blend this. They assume recent time series is helpful, but not too recent. And that's the idea of modeling. So the problem we're going to be working through is really what I've been hinting at this whole time. We're going to try and forecast out U.S. personal consumption expenditure, and specifically the percentage change in U.S. personal consumption expenditure. So to do this, I have basically a data set that you see here, as well as a holdout sample to try and see how well my forecasts and how well the different techniques of my forecasts will actually perform. So let's go with some classical time series to make sure we're solid there, and then we're going to look at a Bayesian approach to these classical time series models. So the first one is going to be the idea of exponential smoothing. Again, we have our two opposite cases that we talked about previously. Everything in the past equally matters, and nothing in the past matters. It makes sense that somewhere in the middle is probably better. That's the idea of exponential smoothing. Essentially, what we're looking at with exponential smoothing is the notion that we're trying to emphasize more recent data. And so we're trying to put more of the idea and the emphasis on current data points than we have in data points that are further back in time. We also want a model that only requires a few parameters to estimate. That's the beauty of exponential smoothing models. They're simplistic in their estimation process. And essentially what we're trying to do is we're going to try and implement this in an easy way. And so an example would be the single, also known as the simple exponential smoothing model, where basically we're applying a weighting scheme across time, where the further and further back in time you go, we're decreasing the actual effect of that data point exponentially. So here you can see actually on the slide the actual equation, but I find this slide to be a little bit more helpful. This is essentially the weight that we're applying to each observation in time. So I want you to focus in on just the dark bars here. So a theta of 0.5, theta being the weight across time. Essentially what we're doing, as you can see, the further back we go in time, where observations t-1 was the previous time period, t-2 was 2 time periods ago, and so on and so forth, that the darker bars put a lot more emphasis on last time period and then very quickly exponentially decrease and disappear the further back we go in time. Of course, we can play around and tune this parameter. We can tune this theta. If we had a theta of 0.25 instead, again, it would spread out that distribution a little bit more. The most information still being on the recent time period, but it allows more information from the past to come into the equation. A very simplistic way of writing the same equation I showed you earlier is actually through what you see here. Basically, our prediction of tomorrow consists of our actual data point today, real data, plus some idea of what we assumed today was going to look like, the prediction of today. So we have our prediction of today, y hat t, as well as the actual today, yt. We're going to combine those together into our prediction tomorrow. This isn't Bayesian. This is just classical frequentist time series. But as you can see, it has all the touches of Bayesian analysis sort of sprinkled in, right? I have real data. I have previous thoughts. Take your previous thought, combine it with real data, and you get an idea of what we're going to be looking at tomorrow. How do we estimate? How do we tune this parameter? Typically, we use just a very basic one-step ahead forecast error approach. We look at the sum of the squared errors, but again, we're doing it one step at a time. We're going to use today to predict tomorrow, see how wrong we were. Going to use tomorrow to predict the day after, see how wrong we were, and so on and so forth from the beginning of our data set through the end. We're going to look at those one step ahead forecasts. And when looking at the errors of those one step ahead forecasts, we're going to try and minimize those errors. That gives us the idea of the single exponential smoothing model. And this is the actual forecast of US personal consumption, again, percentage change, from the data set that I showed you, zoomed in on our whole data set. So the dashed line that you see, which is actually a horizontal forecast, not an exciting forecast, the dashed line you see is my forecast of what US personal consumption would look like, where the actual dotted line is the holdout sample. As you can see here, not perfect, but it gives us a starting point. I find that exponential smoothing models are great initial models to build for time series. They're quick, they're simple. You can incorporate seasonality, you can incorporate trends. Our data did not have that, but they're easy to incorporate and use. All right, so now let's grow this a little bit more. Why should we limit ourselves to an exponential decrease when it comes to the effect of these observations over time? Let's look at what we call the ARIMA class of models. The ARIMA class of models corresponds to two pieces, the AR and the MA, hence the name ARIMA. So the AR refers to autoregressive models. Again, what we are basically saying with autoregressive models is we can forecast a series based solely on past values. And that's the idea. We call these past values lags. And when we're looking at these lags, we're basically saying, I'm going to predict tomorrow using information from today, yesterday, the day before, and so on and so forth. However, I'm not going to assume a weighting structure. I'm not going to assume an exponential decay of weights over time. I'm going to let all of these weights be independent and free. Essentially, the weight of yesterday is going to not be affected by the weight of 2 days ago and the weight of 3 days ago. They can be whatever they'd like. Again, not an exponential pattern that I'm forcing onto it, which means I'm estimating more parameters here. These are what we refer to as long memory models. They have a tendency of holding pattern longer into the future. The flip side of that coin are what we call moving average models. That's the MA piece to ARIMA. The idea of moving average models is we're actually forecasting a series based on the errors of the forecast that we've had previously. We call these things error lags. You can think about the idea of me trying to forecast tomorrow. I'm not going to be perfect. I'm going to be wrong. The error that I make in that forecast is actually going to permeate to the next day. That's the idea of what we're working with here. Without getting too far into the advanced mathematics behind this, just because of time's sake, essentially the ARs and the MAs work oppositely of each other. An MA model is what we call a short memory model. It captures short-term effects where the AR captures long-term effects better. Of course, why not combine all of these things together? Maybe we have some long-term effects and short-term effects. That's the idea of the ARIMA class of models. You're combining both the AR process as well as the MA process simultaneously. These quote unquote mixed models are typically used to try and reduce the number of parameters. So maybe I could model this with an AR, but it's going to be a lot of parameters that I have to model. But if I did an AR and an MA together, it will reduce the number of parameters. That's the idea. Now, you may be thinking, what about the I? I skipped the I in the middle. That actually stands for integrated. ARIMA models are actually formally what we call stationary models. I'm not going to get into the concepts of stationarity. If you're interested, though, I actually have a YouTube channel that explains all of these concepts in like under 5 minutes. So feel free to check that out. But the idea of stationarity is quite simple. We're basically saying here that the series doesn't have any seasonality or trend to it. It has a tendency of hovering. And that's what we're assuming. Since our US consumption data set has a tendency of hovering, we don't have to worry about this here. So we're sort of going to ignore the I piece to the ARIMA model. Awesome. I could explain all the different nuances to trying to estimate these things, but algorithms have come out that makes this so much easier. We're going to use automatic selection techniques to be able to do this. I prefer to use the programming language R when doing time series, but you can use a variety of things. Python has a lot of these built in as well. So it's just something that I'm going to show you a couple of different things here. R has two main automatic selection techniques for time series data. The first one called the MINIC. This is in the auto.arima function. And the second one called the ESACF with a function basically matching the name. In case you've never heard of these before, let me give you a brief idea of what they're doing. The MINIC is actually really simple and really straightforward. MINIC stands for minimum information criterion. Basically, what we do is a grid search across AR and MA terms in combination with each other. And what we're going to do is we're going to find the model that has the lowest information criteria. Here, typically, we use something like BIC. So, for example, with our data set, our model had the lowest BIC with the 3 AR terms and 0 MA terms. So that's basically the idea of what the MINIC is doing. It's just a grid search algorithm to try out a lot of different types of models, calculate the information criteria from each, find the minimum. The ESACF, also known as the extended sample autocorrelation function, it works a little bit differently. It's a little bit more complicated. Essentially, we know that AR and MA terms are related to each other. What the ESACF is doing is it filters out the AR terms until all we've got left is the MA piece. If we filter things and there's still more autoregressive pieces, then we haven't filtered enough. So we essentially want to try and find the smallest amount of AR terms we can filter out that leaves only MA terms. And that's going to give us our model. Again, really complicated in how they're trying to approach this and how they're trying to do this. In all honesty, for our data set, the MINIC works really, really well. The other one, you're supposed to be looking for right-hand triangles in this plot and a variety of different things. There are no triangles here that I can see very easily, so we're just going to jump straight to the MINIC. Awesome. So long story short, automatic selection techniques, ARIMA models, it tells us that an AR3 MA0 model is the best model for our data when it comes to this ARIMA class of models. Perfect. Let's go ahead and build one of those. I built one of those. You can see the forecast here. Again, dashed line is the forecast, dotted line is your holdout sample. Now, you have to look carefully here. It is not a horizontal line. So the exponential smoothing model was a horizontal line. This one is slightly diagonal going downwards. So hopefully a little bit better because it looks like my data is slightly diagonal downwards as well. Now, I mentioned at the very beginning, we can bring in external variables as well to be able to help us try and predict things. That's the idea of what a vector autoregressive model can actually do for us. So it deals with the notion of multivariate time series. Multivariate regression is not multiple regression, People confuse that all the time. It hurts me a little. So what we're essentially doing is we're trying to predict multiple target variables at the same time. You may be thinking, how is that helpful? Let me show you. Essentially, we're going to extend this ARIMA class of models. So I'm going to try and predict two things. I'm going to try and predict US consumption, and I'm also going to try and predict US income. So I'm going to look at changes in personal income at the same time that I'm looking at changes in personal consumption. Now, why would I do that? I would do that because I think they're related. I think as one moves, the other moves. So if I can get an idea how US income changes, I can also get an idea then on how US consumption changes. So I've shown you some matrix mathematics here on the screen. Let's just write this a little bit easier for us to understand. Essentially what we're looking at in the first equation would be something like predicting consumption today. And consumption today is going to depend on two things now. Consumption yesterday and personal income yesterday. So we're looking at now the effect of income as well as previous consumption on current consumption. The second equation is the same idea. I'm predicting future income with previous income as well as previous consumption. Now, if you don't actually care about the second equation, that's fine. We can just focus on that first equation. So we can build this model that understands that both of these things move together, but then just look at the forecasts of one of the pieces. That's all I'm doing here. So I'm going to build a model that tries to relate the previous values of income as well as the previous values of consumption to predict the current consumption. Ooh, okay, dashed line, still a little bit diagonal, still a little bit down. Doesn't look like income actually helped change the forecast too much. So that's basically the extent of how a frequentist would approach things. Let's throw a Bayesian adaptation onto these models. How would a Bayesian view an autoregressive model? That's the question. So remember, I have an autoregressive model, an AR3. 3 lags of consumption trying to predict what current consumption is. A way a Bayesian would look at this, though, would be a difference of assumptions. So again, Bayesian are still trying to estimate the same thing. I'm still trying to estimate these weights, these parameters. I'm still trying to tune how much weight do I give to lag 1? How much weight do I give to lag 2? How much weight do I give to lag 3? And so on and so forth. I'm still trying to answer the same question of how much weight do I put on each of these time points? The real question, though, is what assumptions are you willing to make? That's where the frequentist and the Bayesian approaches things differently. See, the frequentist would say, I know nothing about how these relationships have existed in the past. A Bayesian would make an assumption around these parameters. So a Bayesian would say, you know what, the relationship between lag 1 and the current time period follows some prior distribution. Now I'm going to take that prior distribution, update that prior distribution with the data that I have, and that's going to be my new guess on the relationship between, again, my lags and my time point. Same idea as a frequentist, we're just making some prior assumptions. We're also going to make some prior assumptions on Y itself. Y, again, consumption, has a distribution. See, there's a reason I showed you those cross-sectional charts at the very beginning of this talk. Y itself has its own natural distribution. That's going to be something we want to also account for. I want to predict what future Ys are going to be using past values of Y. But looking at just the overall idea of what Y looks like in general is helpful. I don't want to predict something that looks too far outside of the norm of Y if my data doesn't tell me to. So as you can see here on the slide, again, I have that distribution of Y. I also have a QQ plot here to try and understand if this distribution follows an approximate normal distribution. And let's be honest, this is where statisticians sort of use our little waving hands magic. Let's imagine I look at the data in the QQ plot, but I remove some of those outliers. We had some years of really bad US consumption. So that being the case, if we were to remove those few data points, the data is approximately normal. Now, you may disagree, and that's fine. You can put another distribution here as a prior thought. I'm just going to use the idea of normality. Perfect. So in summary, what I have to do if I'm a Bayesian is I have to make some assumptions on some things. I have to, first of all, assume something about the target variable I'm predicting. That first assumption is going to be the idea that Y follows a normal distribution. Well, where is Y's normal distribution centered? Again, this is where the time series comes in. I think the average of this consumption still depends on previous values. So the previous values of consumption impact the average consumption in the future. Then I'm also making some idea around the actual parameters themselves, the relationships themselves. I'm going to assume these tuning parameters, these weights, these coefficients, these alphas, essentially follow normal distributions, centered at 0. I'm going to assume there's no relationship actually until I can prove otherwise. I just assume that there's some normality to this distribution. When it comes to variance, we have to make an assumption there. A typical thing we look at is a gamma distribution because of the right-tailed nature of it. Don't worry as much about the gamma assumption. The real big assumptions here are the assumptions on the data itself, the consumption, and the actual AR parameters. Perfect. So great. I have this previous thought. Then I've collected my data. Let's see what happens. This is my forecast of tomorrow. This is my forecast of the next time point. But remember, my forecast of the next time point is actually a distribution of forecasts. Do you remember how we looked at that idea of all of those samples that we were doing? And all of those samples were different possibilities of what the forecast could be. What you're seeing here is a distributional view of all of those samples. This is that Monte Carlo Markov chain. Right, so here are all of the samples on my guess of what the relationship is, as well as my forecast of tomorrow. Perfect. So my forecast of the next quarter is what you see here, this distribution. So what's my best guess? I'll just take the average. Let's take the average of this, which gives you an average personal consumption of 0.84, so a 0.84% change. And that is going to be my forecast of the next time period. Now, my holdout sample had 7 time periods, though. So as you can see, I'm going to need 7 different distributions. And so we can basically look at these distributions, and they're all different. I know it kind of look the same, but they're all just a little bit different as you forecast into the future. And I'm going to look at the average of each one of these distributions. And the averages of each of those distributions is the dashed line that you see here. This dashed line is my forecast. Again, but from a Bayesian view. Awesome. So I've looked at a Bayesian approach. I've looked at classical statistical approaches. Let's throw one more into the mix. Bayesians also have a vector autoregressive version. We can do the same thing that we did before. We can approach this from a multivariate standpoint where we're bringing in income too. So we have income also inside of this equation and inside of this effect. Same idea. I'm just going to go through this one rather quickly. Have to make some assumptions. The only difference here, I'm assuming a multivariate normal distribution instead of individual ones. we get this forecast. Now, all right, here we go. The thing you've been all wondering, time to compare. Who wins, the frequentists or the Bayesians, right? That's what everyone's been wondering this whole time. Well, let's take a look. Let's look at our forecast of the actual holdout sample for each one of the models that I showed you. Remember, I showed you an exponential smoothing model. I showed you an autoregressive model, a vector autoregressive model, a Bayesian autoregressive model, and a Bayesian vector autoregressive model. I've shown you 5 different models. And lo and behold, the Bayesian autoregressive approach has the best holdout MAPE. Again, the average percentage error. That's the idea of MAPE, if you haven't heard of it before. So it appears to be the model that worked best. But so now you're thinking, of course, the Bayesian had to win. The title of the talk was Bayesians Come to Time Series. Of course the Bayesians were going to win. But see, I've been playing a trick on you this whole time. In reality, what I wanted to show you was the fact that although Bayesian models are good and although frequentist models have their place, in all reality, the big takeaway I want you to think about when it comes to this talk is what if? What if we ensembled both approaches together? The idea of an ensemble in time series is quite simple. You take the forecast of one model, take the forecast of another model, average them together, and maybe, just maybe, both of their opinions together mean more than either one of the opinions individually. So I have here on the left-hand side, the AR3 model. I have on the right-hand side, the Bayesian version of that AR3 model. What if we were to ensemble them together? This is the forecast that I would get. Take a look before the forecast, before the shaded area. I want you to take a look at the left-hand side of this chart, the actual training data. Look how close my model is at predicting this training data. You might think, well, this may be overfit. Well, that's why we have the holdout sample, right? So we can take a look on the right-hand side and we can see here, actually, the ensemble of both of these approaches, both Bayesian as well as the idea of ARIMA models, actually helped improve things beyond what any one of them could have done by themselves. Awesome. So I know we're running a little short on time here. I'm more than happy to sit around and answer any questions you all have. Thank you very much for allowing me to come out and talk to you all today about the idea of how to incorporate Bayesian approaches to time series and ways to integrate all of these things together. Thank you again, Bill.
Thanks, Eric. That's great presentations. And let's go jump into the Q&A. I see a few questions in the chat, if you can open up. And just quickly remind everyone, please post your questions in the chat. And if you prefer to speak, ask questions, or even want to comment, and feel free to raise your hand. You can speak to ask questions too.
Awesome. Well, going back to the chat, I see this here. The first question that I saw come in, going back to the beginning of the talk, what about when y is dependent on the x's? What kind of model would we use then? Well, that's actually what we're hoping for in any kind of machine learning model or any kind of approach, right? We're hoping that these x's have some impact on y. Otherwise, it's not going to be too helpful for us, right? We're hoping that other variables that we can collect will actually try and impact the target variable that we're interested in. So really, it's now a matter of what your data is structured as. If your data is structured as time series, we can use time series to relate x and y. If your data is cross-sectional, we can use other machine learning approaches to relate x to y. So hopefully that helps there. Another question that came in, when you were on slide 34, you mentioned BIC. What is BIC? Oh, yeah. Bayesian information criterion. It is a common way of being able to compare models. Think about the idea of information criterion as how much of the noise of your data is explained by the model. That's essentially what we're trying to do. And so we're looking for this notion of finding the best model. But we penalize ourselves for having too many variables. So that's the balance trade-off that we're trying to approach. Just a way of being able to evaluate models. You can think about it like another approach to root mean square error or anything like that. Let's see here. In my experience, ensemble is useful with 5 or more heuristics. Yes, ensembles are great. And in fact, a lot of times, in all honesty, the more the better when it comes to this. Really, here we only chose comparing and combining 2 models because it actually didn't help us to combine all of the rest of them. All of the rest of the models really provided the same kind of information. In fact, let me go back to the slides here for a moment. You can almost see, especially when it comes to the vector autoregressive, the Bayesian vector autoregressive, the simple exponential smoothing model, they're all providing pretty much the same information. And since they're all providing around the same information, combining those together really didn't add anything to it. So hopefully that helps as well. Let's see, how can you compare AR and BAR if I could have assumed any prior? Do the results depend on the prior assumptions? Yes, Sven, they actually do depend on those prior assumptions. Now, the more data you have, the more it'll force you off of those prior assumptions. So if you have a ton of data, you can pretty much make any prior assumption you want, and you would be able to get away from that prior assumption. If you have a limited amount of data, though, you're going to be a lot more closely tied to that prior assumption. So the priors do matter. I don't want you to think that they don't, but the more and more data that you have, the data will have a tendency of outweighing it. So don't feel too overwhelmed by those assumptions if you have a lot of data. Let's see here. Is a 2% gain enough to say it's better? Great question. So I guess it really depends on how much you benefit from something in that 2% gain. So for example, a lot of times I've worked with banking data. So when it comes to banking data, 2% can mean millions of dollars worth of swing one way or the other. So it really depends on what you're looking at and that scale. You're right. Sometimes 2% may not be too much of an improvement. And if I have to build 2 models to get to that 2%, maybe that one model, the Bayesian autoregressive model, would do close enough. So that really evaluates based on how much you've got to be able to play with. Let's see here. Charlie, did you use BSTS by any chance? I did. So BSTS was actually the package that I used to be able to build this in R. So yes, great package to be able to combine things together. And if anyone's interested, feel free to reach out to me on LinkedIn or something like that. I'd be happy to share the code on how I built all this. Really simple, really easy. Let's see here. Is there any pre-processing that you need to do to the data before passing it into the model? Robert, it's the same kind of pre-processing that we always have to worry about. So missing values in time series can be a little bit of a headache, just like with regular data, because you're sort of missing gaps in time. And if those gaps become too large, you start to lose an idea of what's happening across time. But it's this typical same kind of pre-processing. Let's see here. In the ensemble model, is the weight for the Bayesian and the Frequentist 50-50 each? And we have William wondering if there was a way to actually tune the weights to find the best quote unquote ensemble model. Yes, so I took the simple approach of basically assuming a 50-50 weight on each. Another way of doing that is a weighted average. And the best way to account for that is basically you would have your target variable is your actual holdout sample, and you would do a simple linear regression. Well, not simple as in one variable, a linear regression that has your 2 forecasts together. And you would basically limit the parameter estimates of your linear regression to be between 0 and 1. And then essentially what it'll do is it'll weight those 2 things in combination to give you your holdout sample. So that would give you your optimal weight when combining those 2 things together. For forecasting demand after COVID reopening, how effective Bayesian is going to work given the prior year 2020 may be an outlier in terms of demand? How would you forecast in these cases? So great question when it comes to these things. I think Bayesian is actually extremely helpful in these scenarios because of the fact that you have a lot of data potentially that informs that prior. But if you don't have a lot of data that deviates from that prior too drastically, the model will still lean on the things that it knows and has learned from the past. So I think Bayesian approaches, especially when it comes to outliers, have a lot of tendency to do well because the outliers will pull it a little bit, yes, but it has something at least to lean on. A frequentist approach, if you were just analyzing data only in a frequentist world and only using COVID data, you'd be stuck a lot more than you would ahead of time. Of course, you could always just ignore and throw out that piece either way. Let's see here. What about deep learning? Sure, deep learning has its approaches as well. So, I mean, what about deep learning is a question that we could talk about for hours. So I don't know, Dan, necessarily what more you would be hoping from that. So if data is a time series, then how do we incorporate x1 to xn in the model? In this talk, y was dependent on previous y's only. Yes, they were dependent on previous y's until we incorporated those multivariates, right? So when we looked at the idea of the multivariate time series, we were looking at past lags of income as well as past lags of consumption to actually forecast future consumption. So there are time series models that incorporate them together. There are also what we call ARIMA X models or Bayesian ARIMA X models that just bring them in directly into the actual large equation. So hopefully, as if that helps out as well. So next question came in, if I try stuff like Profit or Pyro. Personally, I'm not a big fan of Profit. I know that it's probably bad to say, but it's one of those things where basically what Profit uses is the idea of a bunch of Fourier analyses to be able to pick up some seasonality and trends and then some basic lag structures in there. It's one of those things when looking at something like the Profit algorithm, it's a good algorithm, it works, but I find these other models to actually be a little bit more interpretable potentially than Profit. So that's why I have a tendency of not leaning on Profit. I can get just as much I have, at least in my experiences, been able to get just as much predictive power outside of Profit than I have with Profit. So it is what it is. What Python package do I recommend for Bayesian time series? Oh man, for Bayesian time series, I'd have to think about that for Python. Dave, reach out to me on LinkedIn because that's something I'm not sure of. I know R has a lot of them, but when it comes to Python, Python is new to time series. So that one I'm not as sure about. What Bayesian methods are there for non-stationary time series data? Same kind of approach. What you only have to do is just make your data stationary first, and then you can go with all the Bayesian approaches. That's what ARIMA models do. You basically take data, make it stationary, apply stationary models, and then convert it back. So you wouldn't have to necessarily change anything about that one. Oh, wait, let's see here. Sorry, wrong typing. Is there a GitHub? Oh, for this, there's not a GitHub talk. It's something I guess I could throw out there if you guys are interested. But again, feel free to reach out to me, email, or let me throw my email back up again. Email, LinkedIn, I'd be happy to share the code. How do I feel about interpolating with missing data points? I love interpolation in time series a lot more than I love interpolation outside of time series. In time series, I know what happened before and I know what happened after. I can connect those with a straight line. Interpolating outside of time series, I find is a very dangerous thing because I don't know what happened before and after. I don't have context. So I love, actually connecting dots in time series. And then I know we're running a little bit out of time, so let me just answer a couple more. So how do Bayesian models scale with data dimensionality? Could they be used for thousands of parameters, or would the prior assumptions interpret non-correlated parameters as signal? Bayesian models, the one thing you have to worry about is the computational oomph that is required for Bayesian models. That's the one thing. Bayesian models have become a lot more popular lately because of the fact that we have computational power to handle them. But if you're going to do this at large scale with thousands upon thousands of models, that may be something that'll be a little bit more computationally intensive than if you were to do that with a frequentist approach. So just something to think about, Paulo. All righty. And then any suggestion for a paper document explaining MCMC? Oh man, I don't have one right off the top of my head, but in all honesty, and this is scary to say, Wikipedia has some really good initial pieces of information, and their sources at the bottom for a lot of statistical concepts are actually relatively good. I think it's just because no one knows they exist on Wikipedia, so no one goes in there to screw them up. So that's probably my best place that I would start if you want some good actual citations on MCMC. But that looks like it's covered a lot of the questions. So again, thank you all very much. It was a pleasure talking with you all today.